Word problem. Okay, so we're moving. I'm just going to tell you applied math. We focus on word problems. So this was just an activity to get you used to, right, the different functions, how to graph them in general, because it could show up. They do ask questions just in general, but then most of everything else is word problem related. Okay, so we're going to deal with equations are provided. And so I'm going to do quadratic and cubic, hopefully, by the end of today. So grab your calculators. First things first. Well, I should probably read the question and then we'll enter it. The path of a baseball that has been hit can be modeled by the following equation. And there it is. And notice that it's not y and x. Its height in terms of time is, right, this is the equation that will model the path, where ht is the height. Okay, we always know that this is our y. Whatever's on the left side of the equation is the y, and this is our x variable. Okay, and so ht is the height in feet, and t is the time in seconds. This is x, this is y. So they give you y first, then x. Normally that's convention. But we want to go, we know that every single point on this resulting parabola will be time followed by height. And I know I'm going to oversimplify if I say this, okay? But 80% of the time, it revolves into them giving you the time, figure out what the height is at that time, or they will give you a certain height and they want to know how long did it take to get there. Honestly, like most of the time, that's what you're dealing with. So if you figure out what your variables are, and that this is x and this is y, this is going to be along your x-axis, along your y-axis every single time, the rest is easier to interpret. Okay. We know it's asking us for the initial height. I'm going to highlight that part, the keywords, the initial height of the trajectory of the ball. In other words, at what height was the ball hit? They have a mind of their own sometimes, these phones. Given by the y-intercept. Given by y-intercept. Okay, which is 0, 4 in this case. The y-intercept is 0, 4. Okay, so you can't just leave it like that. It will be, it was hit at a height of 4 feet. Let's see, of 4 feet. So it's that 4 that we're after. Some students just answer 0, 4. You're close, but not yet. It's almost like you need to give me the answer. Like, which one is it? It's that one. Okay. So at time 0, you're at 4 feet above the ground. Does that make sense? At time 0, if you've done physics or anything like that, I think this makes sense. But if you haven't, now it should make sense. What's the maximum height of the ball? So we're going to go the vertex. This is given by the vertex. Okay. So we're going to go second, trace, max, maximum. I just write down max most of the time. So now we need to actually graph this thing. We know because of the leading coefficient being negative that this is pointing down. So let's go ahead and type this in. We're going to go negative 4.9 x squared plus 35x plus 4. And we're going to hit graph. And let's see what happens. I can see, yeah, it's not a really good graph. So you either go window and change those, or zoom fit. I'm going to go with the window, and this is why. Okay. I'm gonna, since this is a word problem, I'm gonna add that since this is a word problem, we stick to quadrant 1. We stick to quadrant 1. In this scenario, okay? In this particular scenario. Why is that? Because time cannot be negative. And is the ball going underground? Not as far as they're telling us, okay? So that's why I'm going to say, okay, I'm going to grab my calculator window. What I'm going to change is my x min. I'm just going to have it slightly towards the left of the y-axis. And my y min, I'm also just going to have it slightly underneath the x-axis. So if you do that, that's kind of standard. I do that a lot. Then you're good. Now, let's hit graph again. Let's see if this improves it. It has improved it so that I don't see too much in the other quadrants, but there's still lots of dead space here. So this is x max, folks. X max is 100, and I see way too much. So I'm going to go 20. My y max is also too far up. So I'm going to go 50 for now. I'm just guessing here. I'm going to hit graph. And I did okay with my x max bringing it to 10, but I kind of cut it off here. So guess what? Go back to y max. Let's go 100 there. That's a pretty good graph. You could still trim a little bit, but you know what? We're not going to waste too much time on that because it's just to help you find. So let's find the vertex now. Second, trace maximum. Go to the left of it. Go to the right of it. And there it is. So I'm going to state my vertex here. 3.57, 66.5. So guess what? At a time of 3.57 seconds after being hit, you're getting to the maximum height, which is 66.5 feet. Okay, so we'll say this. Max height is 66.5 feet. You got to make sure you have units if you want to get it right. How long does it take for the ball to hit the ground? You can also say remain airborne. This is the x-intercept. And we're going to find this by going y2 is equal to 0, second, trace, intersection. So let's go ahead and find that. So the ball hits the ground right here on the x-axis. So I already have y2 equal to 0. But if you don't, you just do that, hit graph. Then it's second, trace 5. And you're going to just get close to it. Enter, enter, enter 3 times. And it's 7.26 if you round it. 7.260. So that's when the height is 0. That's when you hit the ground, correct? So it takes 7.26 seconds. There we go. So earlier we would just find the vertex, find this, find that. Now they have a meaning. They have a meaning behind them, okay? Okay. Calculate the height of the ball 1.5 seconds after being hit. This is what this question is saying here. When x is equal to 1.5, what is the height at that point? What is the height at that point? We're going to use this function, second trace value, right? That's the first option. And we're going to let x be 1.5. Spacing is not really good on this one. It feels very cramped. I'm going to have to edit that. Second trace value X is equal to 1.5 seconds, and there it is. Y is equal to 45.475. You can leave it like that because it's not dollars, but you could just say, hey, I know that this is the height in feet, and then you're good to go. Or 45.48 feet. It's up to you. Here, determine the time the ball remains at or above 49 feet. I don't know if you remember this from grade 11. You remember delta t, delta time? Finding the difference between the times? Some of you are nodding. Way to go. The summer didn't erase your good memories. Must have been a good memory. Okay. So what happens here is, I'm going to give a little sketch here. I like having a little bit of a sketch for this. I'm going to zoom into that part. Some of you are squinting. So the ball is hit at 4 feet above ground, and then it goes like this. And at some point, it does hit the ground. We already figured all those points out. But we want to know how long does it stay at 49 or above. So guess what? We let y2 equal to 49. Let's do that all together. That's our reference point now. y2 is equal to 49. Hit graph. And there it is. That's the 49 line. So I'm going to find out what time does it happen first on its way up. And then I'm going to find the time when it comes back down to 49. And I'm going to subtract those two. That's how I know how long it's spent above that, okay? So I'm going to go second, trace 5 for intersect. And I'm going to go time 1 and time 2. Let's go ahead and find those. So second trace 5. I find time 1. And here's one thing. If you want to get full marks, don't round to 2 decimals yet, because this is not your final answer. Go 4 decimals minimum. Okay. Second trace 5 again. Enter, enter, enter. That's 5.4613. Okay. Before I do the math here, let's go to our sketch here and kind of copy what's happening. This is the 49 line right here. So this is time 1, and this is time 2. Time 1, time 2. So the difference in that time will tell you how long. Because you could say, hey, it happens at 1.6 seconds or 1.7, and it happens again at 5.5. We could say that, but we don't know how long right now. How long was it between here and here? Okay, so we're going to go delta t. Assume 5.4 minus 1.6. Delta t is just take the difference, right? What's the difference in time? And I already have this, so I'm just going to go 3.78 seconds. This is how long. This is usually a 2-mark question. If you have to find the times and subtract, it's usually a 2-mark question. I'm just going to say, right, this tells you how long it was above, at or above. Let me say it one more time in a different way. When you subtract the times, you're actually figuring out how long did it take to go from one to the other, right? So in this case, you were above, but it could have been a dip like this, and in which case you would have found out how long was it below, okay? Common sense, read the question. Let's graph this now. So here, it's a word problem. Okay, watch. It is a word problem. Okay. Quadrant one, I'm not going to say quadrant one because we will consider cases where you do go underground. So I'll just say watch, it's a word problem. That's all I'll say here. So now I'm going to the graph. So what needs to be on the axis? X and Y isn't going to cut it anymore. Okay, so you got to go time in seconds, very important. And then y-axis is now height in feet, right? So it could be feet, yards, meters, centimeters, you name it. And now we're basically going to do the same as before. We're going to come up with our intercepts, our vertex, the important points. So what's my x-intercept? 726, correct? So I'm going to try this. 2, 4, 6, 8, 10. That works pretty good. So that's the scale that I choose. And the highest point that I need to include for the y is 66.5, correct? That's the highest altitude. So let's see here. Is this going to work if I go up by tens? 10, 20, 30, 40, 50, 60. I'm going to go up by 15s. Uh, 60, 75. So make sure you mark where the labels go, okay? Probably not ideal to go up by 15, but that's all right. So let's 0, 4, correct? This is 7.5. I guess we're going up by 15 divided by 4. Okay, so that would be right about there. 0, 4 is there. And then 7.26, this is 7. This would be 7.5. So 726 is right about there. And the vertex happens at 3.57, the highest, right? 3.57. This is 3. This is 3.5, so just right of it. And I'm going to go all the way to 66 here. So this is 60. Be 67.5 here. So just under it. There. And then you go from the vertex, curve down. And then from the vertex, go out a bit and then curve down. This is going to be h of t, negative 4.9 t squared, plus 35t plus 4. That's it. That's all you need. No arrowheads, okay? In this case, no arrowheads because it starts at when it gets hit, and then it models the path, and then it lands on the ground, and so that would be it. We wouldn't have the bounce, 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 right? We wouldn't have that part. It just stops there. State the domain and range of this scenario. We assume that the ball stops upon hitting the ground. Time is your domain. And height, whatever's on the y, is what we're going to use for our range. What's my domain here? Brave volunteer. Time starts at 0, correct? And it lands after 7.26 seconds. So that is your domain. Right? It starts at time 0. This is technically 0 here, and all the way to 7.26. So that's my domain. My range, make sure you square brackets when it's numbers. When there's infinity symbols, it's a round. Okay. For range, what's the lowest height I possibly get to? The ground, which is 0. It's not landing on anything, right? So you go 0. And then the highest point ever for the height is 66.5. Outside of this, nothing happens, right? You don't go into the negatives. You don't go higher than 66.5. I will do this. I don't know if I did this in the notes, but for the domain here, it's basically and for the range, you kind of look, where's the graph? It's still there at 0. So you keep going until you reach that highest point right here. So I'm going to actually do this. If it helps you, I don't know, I feel like it might label this with the actual coordinate, right? So it's this, the y value that determines. Oh, set notation. I should do that too. Or here's the kicker. If you want to use set notation, you go 0 less than or equal to. What is the variable for x in this case? Look at your equation. It's t, correct? You have to use t. Sorry, I know this is very crowded. I don't like that. So make sure you use the squiggly brackets. So, or this one you could state 0. You can use h or you can use h of t. It doesn't matter. The province will accept both. I don't need you to be able to necessarily write it in set notation, but I do need you to be able to read it. Let's say it's a multiple choice and they say which one is the range for the situation. I would expect you to read this and know what this is saying. Okay? But I'm not going to force you to use set notation over interval. Okay? Almost done. I was going to do cubic today, but I'm going to stop at quadratic. State the domain and range of this scenario. Watch this. Let's highlight that. Assuming that the ball was caught 6 feet above ground. So almost like a whole nother problem. So let's sketch this. You know it starts at 0.4, correct? It gets launched, it gets hit, it reaches the maximum height, and it will land. It's caught at what? Something 6. We know it's 6 feet above ground where it's caught. Does that make sense? What I just did there? That's the scenario here. We still know that this is 3.57, 66.5. That hasn't changed. We're just saying, consider the exact same circumstance, exact same path, but now it's caught. So let's do our domain and range for that. Can we do our domain right now as is? We know it starts at 0, but what time is it caught? We don't know. How can we find out? I'm glad you asked. I thought you'd never ask. We're going to figure that out. off script here, hold on. I'm going to figure out what that intersection is. I'm going to know both coordinates in a bit. So I'm going to grab my calculator. I'm going to make y2, I'm going to make that equal to 6. And hit graph. And there's my 6 line, which allows me to find that time there. Second trace 5. Go closer to that one. That's 7.09 according to my calculator. So 7.09 seconds. Okay. So this is where the action ends. When it's caught, that's 7.09 seconds. What is my range? Four? Yes. That's the lowest ever. What's the highest? 66.5. Yes. So I can honestly put down, I can probably put down $100 that on the exam, at some point, they're going to ask you for domain and range. Like it's almost inevitable. So that's why I'm going to ask you a lot, and I'm going to kind of put a twist on it so you can, keep thinking about that. Okay, one last one, and then we're done. Then I'm going to give you your homework. Write another equation. This is also classic. That would model the path of a ball with a lower maximum height. Here's one example. I will copy everything exactly the way it's given up there. But guess what I'm going to do here? Anybody? I'm going to outsmart the person writing this question. I'm going to say, take that. Take that. It's a little lower, right? You could have done anything. I will just say decrease the y-intercept, which is because this could have been used for a cubic as well, right? A cubic function, just decrease that y-intercept, because if you do so, the whole thing shifts down. The whole parabola is just slightly lower. If you're ever not sure if your equation meets the criteria, enter it into y2, graph them both. And if you can clearly tell that yours is lower than the previous one, you're going to get the mark, right? So it is possible to achieve this by changing A and B as well. But I'm not going to, I think this is just the easiest way to do that. Okay, I'm going to stop here. Was about time, wasn't it? I'm going to ask you to, if you could write this down. I don't know, I think it's better on 26. Let's go to 26. I'm going to say page 26, and there's another quadratic. Yeah, the one that's pointing up. So 29. And page 29. Okay. So do both of those quadratics. One more thing. I know you're going to be like, more. Page 23. You can do this if you're in the car or on the bus on your way to school. You can probably do this match equation to graph. That's what that is. I would really want you to be good at that. And I'll show you before we go home. I'll show you on the screen what I mean. So 23 has a bunch of graphs, and 24 has a bunch of words. So you kind of want to match the graph with the corresponding description of it. Okay, so you're gonna have to watch carefully and take your time on that one. I will post the key to all of that. Maybe not the matching, but for sure 26 and 29.